Let's make sure this is working as intended. Yep. Boom, 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 boom. Do 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 do. Hope you're excited. I'm excited. It's been a long time coming. Just make sure Zitvich is set up as I intend. Yeah. In fact, we are missing one here. Let's add that. Chanel. Go. Mute you. Pop out you. Pop out. Which means you should pick it up. Sort of. Yeah. Pretty skewed, isn't it? Hey, there we go. Testing. All right. So, welcome. I've been talking for a long time about doing more engineering. And while there are a huge number of topics that are still more software oriented, I would love to do at some point. I figured it's time I hold myself accountable. And that's one of the reasons this has been taking such a long time coming. I was stuck on a very interesting project and still am. In which I wanted to take a Docker file specification of a system and use it to build a custom image for a cloud provider. So there are a lot of other things that go into that. It's mostly successful, mostly succeeding right now, but there's still a few issues with, in particular, like the cloud init configuration that's work in progress. But maybe we'll get to that at some point. But I've pushed this off long enough. It's July 24th. I'm way behind on my 1-a-week plan. So we're just going to go ahead and the engineering stuff started. So let me start with a little bit of a background. Way back, I took Latin in high school, but I only took the first 2 levels, and I took them in 1 year. And I took them with like 6th graders who were gonna, had 6 years of Latin ahead of them, and I was in my senior year. So basically, it was like, let's learn some more language and polish out verbal section of SAT knowledge, right? Word roots and all that stuff. So I needed a way to really accelerate sort of my Latin learning long before Duolingo, right? This was 2002, 2003. And so since I was learning to program like C and GW Basic at the time, I put together a little quiz generator. That quiz generator basically was just like a vocab test, right? So given this word, this translates to that Latin term, or vice versa, or maybe this, conjugation of this verb or this declension, etc. So it wasn't particularly crazy, but it was amazingly effective. And half of the benefit, I'm quite sure, came not necessarily from using this little quiz app I put together, but actually writing it in the first place. It was a very interesting process, very insightful. So I'm going to reapply something like that here. I want to do more sort of basic engineering conversations and talk about more fundamental engineering topics on this channel for the second half of the year. And I figured a really good way to do that and to structure it and scaffold it would be to look at something like the fundamentals of engineering exam and say, okay, let's walk through these sections of these topics and concepts of engineering and do some basics. So that starts with sort of an epistemological discussion, right? Where we're looking at a knowledge base and we're trying to figure out how do we organize this knowledge base? How do we break it down? And how do we do so with pedagogical concerns? How making sure that it's something that we have a structure for learning. And this seemed like a really reasonable approach. Let's put together a quizzer. This is a nice transition from the software to the engineering side of this channel. Let's put together a little quiz generation app that's a little more sophisticated than just vocab, flashcards, that looks at each section of the fundamentals of engineering and breaks it down, not in a super detailed way, but in a way where we can understand what the relationships are, what the key concepts are, and present them procedurally in a way we can test our own knowledge. So we are going to put together a quizzer thing. I took a look at some options. Closest thing to sort of a super lightweight basic quiz thing I found was someone's GitHub project called Light Quiz. I ended up tearing most of it out because it was like calculus pictures based, but it was still the closest thing I could find. So we're going to start with that. But in the interest of keeping to good software engineering practices, we're going to focus on sort of the core function of this first before we worry about logins or UI or how the question goes from one to the next. We're purely going to think about how a question is generated first. And answering that problem is going to take up most of the time conversation today, but it's pretty interesting, I promise you. So let's think about a particular topic. It could be in engineering. Maybe it's materials. Maybe it's fluid dynamics, which is near and dear to my heart. I did a lot of CFD stuff in college. Um, when we typically think about a concept in a field of knowledge that's very technical and physics oriented like engineering, we're typically talking about learning and understanding relationships between concepts. And in particular, the relationships we're really interested in take the shape, or take a couple of different shapes, right? Typically, they'll take the shape of something like an equation. So let's think about equations and think about how we can represent equations in such a way where we can use our understanding of those relationships to generate problem sets, right, dynamically. So might as well sketch some things out here, which reminds me, actually, I need to put this over here for the camera. We need to change the video capture device for this. Let's go to, that is the camera window, display. All right, here we go. If you'll pardon the infinite mirror effect here. So let's consider a very basic equation, right? This is a great example. Very important equation, right? This is the ideal gas equation. And we have some very interesting relationships here that aren't necessarily reductive, right? These aren't degenerate examples. These are really interesting relationships and examples. So in this equation, let's break out sort of how we would graph these relationships. So we have a concept here. We're going to represent in this graph by a node, and that concept is pressure. That concept may have some other things associated with it, like what sort of units to use to measure pressure in it, right? We have another concept here, volume, and similarly, there may be specific units associated with the volume or other relationships, of course. Then we have this concept of, right, a quantity. So in this case, it's a molar quantity. We have, so that's got some sort of units as well. We have a constant, noble gas constant, or ideal gas constant, rather. And of course, we have the concept of temperature. And given all of these concepts as nodes in a graph, we can express or identify this equation as a relationship between these nodes. So this equation defines a specific relationship or constrains the relationship between these five quantities. And there are other ways that you could break this out. That's good enough for now, but you could also say, identify the product of these quantities and identify the product of these quantities, and then assert a relationship that says they're the same thing. For now, we'll just focus on purely understanding what the equations are. So we'll say there is an equation that constrains the relationship between these concepts, and the knowledge of the nature of that relationship and the equality is, internal or specific to that specific relationship. So as you can probably tell here, there's a couple of different kinds of relationships. So if we tried to graph knowledge in a specific area, right, in a specific area of engineering, field of engineering, for example, there's a specific structure that this graph would take. You might not necessarily have a concept attached to a concept, right? A pressure and volume would not be directly related. They would be related to each other through a relationship, and that relationship is basically another kind of node in this graph. And then maybe there's another relationship over here that says this pressure volume and another pressure volume, right, I'm trying to remember what is this. Oh no, this it's not the ratio. PV1 equals PV2. Sorry. You have Boyle's law and other sort of relationships that you could reuse these same concepts but express different constraints or relationships. Now they're not entirely context free, right? But they're enough where if we wanted to go in and look at a definition of this knowledge graph, we could say, let's choose this relationship, right? Come up with, for given these 5 values, one of which, by the way, is constant. So that's another, this is like a membership relationship, right? This is a member of a set of constants, and it will have a specific value. So that's a little bit like its own sort of relationship or constraint. 8 point blah, blah, blah. As are, this has a unit of count. So basically what you see here is none of these things have sort of connections to each other. Rather, it's almost like a red-black tree, right? But it's in graph form, where you have one set of nodes connected to another set of nodes, and there's no internal connection between those sets. So technically, this is what we call a bipartite graph. But bipartite graphs are usually presented in a slightly different way. All we really care about here are the fact that there's 2 sets of nodes and relationships between, for each node of the other set, and for each entry node in the other set, members of the first set. So that's how we're going to build out this idea of a knowledge graph for different fields of engineering. Let me show another example here that's going to introduce some interesting ideas. Let's consider what kind of problems we might want to generate, whether we're looking at fluids or kinetics or statics or structures or anything else. If you are procedurally generating an exam, there may be different kinds of problems you want to generate, right? So we already implied one specific kind of problem, which is if you listen to or watch the video on spicy math, there's this idea where the number of constraints has to equal the number of variables. So if you have 2 variables, you need 2 constraints, or degrees of freedom, right? I think we mainly call them degrees of freedom. And those are basically, so if you have 2 unknowns, you need 2 equations or other ways to constrain those unknowns in order to find unique values for there to be one unique solution. So that's one kind of problem we might have, and that will take the classic shape of, let's say, just as a simple example, in one stage of a thermodynamic cycle, you have some volume of gas, then the pressure is reduced. So what is the corresponding, or the volume is increased, so what is the corresponding decrease in pressure, right? So in this case, basically we identify this relationship. We choose values for all but one variable. And then the problem is, solve for the unknown, the final unconstrained. So obviously in this case, it's 1 Pascal or maybe 1 atmosphere. So this is one kind of problem that's very interesting and useful. And what's more, you can expand upon this quite a bit, because you can recursively walk through that graph. We had sort of a set of relationships of nodes, right? But there were a couple of relationships. So maybe what you have is, initial conditions here, and then some final conditions that you don't know pressure or volume for, but you are also given, another relationship to expand that says there's some, values. This actually isn't going to work, but you're combining equations to sort of walk through multiple concepts. So we're going to treat that as the same family of problem here. Oh, didn't mean to erase that. Just with the caveat here. Yeah, we will erase it. With the caveat that we could potentially recurse through multiple relationships. And we could even use that to find some degree of difficulty for the problem set, right? This is a simple problem set. It only looks at one relationship. This is a medium problem set that looks at 2 coupled relationships. This is a spicy problem, and it involves 3 or more relationships, right? that recursively expand and provides different constraints to be able to come up with some solution. Okay, so there are, of course, other kinds of problems that you'll commonly see on an exam. So let's think about multiple choice. So in this case, you could think of this as a set membership problem, right? Because basically what's going to happen here is for a multiple choice question, there's going to be some assertion, some condition. Let's say these remain constant in, just continue the thermo theme here, in adiabatic and then right, yeah, because that's a great example actually. So there is implicitly a set membership question here related to the assertion. So whether it's one choice or check all that's true or what have you, what we're really interested in here is the set membership. So we have to go back to our bipartite graph here, and this is why bipartite is actually not a very good term, because it's more like tri or quadripartite, where we have concepts and then some, let's see, there are different relationships that describe attributes of the concept. So we mentioned units as one. So this is sort of like, let's use a different symbol for that. This is like, let's say this is a set membership relationship where this concept belongs to the set of concepts that have, units of some volume, right? Let's say that's V. And this is, belongs to some set. And then we'll use this box as sort of, let's introduce equations here, equation terminology, just to be fancy. So there are several relationships that we might want to define in order to construct different kinds of equations. So that's the second kind of problem here. Then the third kind of problem, which is sort of related, is sort of an epistemological problem as a pure assertion. Like there's an assertion. Is it true or is it false? So, Johnny shoots basketball and the ball at its peak is 3 meters high, with some initial velocity. Does it go in the basket? Right. The basic form of the question. So that is interesting combination of these two, because you have some sort of a relationship that you're solving for, and then based on the solution of that relationship, you're checking membership in some set, or is a condition true or is a condition false? So there are other kinds of problems, of course, and we're obviously ignoring the subjective problems. Write an essay about good luck using this to study for the ethics portion of your exam. But this gives us the scaffolding for going forward and constructing a knowledge graph for each field of engineering that we'll look at. So let's start with a very basic change our display capture again. Back to, there we go. Let's start with a very basic modeling question here, which is, given, light quiz or some other field, let's go through each topic area and think about how we're going to define these graphs. For any given graph, you have a set of nodes and you have a set of relationships. So for purposes of consuming these within the application, which is just JavaScript, we're going to say these are CSV. So let's look at the nodes in our graph. These nodes, in this case, we're going to say the nodes have an identifier. We're going to use this sort of a variable, basically. And those nodes will also have a name we use in constructing the actual text, if necessary, for the problem. They'll have some sort of they may, I should say, have some sort of a unit attached to them. And then a particular concept may have a particular type. So the variables, this is how we're going to sort of hack into those different relationships I mentioned, which is The relationships may have different types. There may be an equation relationship, and there may be a set membership relationship. And so some of those concepts may be units. Some of the concepts may be variables, and therefore there will be relationships between the variables and the units as concepts. So you'll see in here units listed as nodes, for example. So in this case, our first topic area is units. So basically, we're going to generate some unit conversion problems. Pretty straightforward, right? So what do we need to generate unit conversion problems? Well, we need some concept of units, and their relationships. So we also have a set concept here, so we can define not just the unit attributes of a particular variable. We also have constant types here, but also memberships. So these, meters will be a membership of the SI unit set, but milliliters will not. And then there is a set of physical constants in this case, and so we can say that the gas constant is a member of physical constant. So let's look at those relationships now. And here's where it starts to get a little hacky, doesn't it? So the one relationship could potentially be, and this is obviously not related to the units topic area, it's primarily an example. So we have like the ideal gas law. That relationship is an equation type relationship. We also have something of, I'm thinking about this in different ways, a hierarchy relationship. There's probably better names for that. In this case, the idea, of course, is that there's a way to convert other units of volume to and from the SI representation of volume liters. So meters is an SI unit. Milliliters is not. So the liters relationship to milliliters is, you could think of it as an hierarchical one where you can convert back and forth. So there is some syntax parsing required here, right? So this is basically what I was talking about earlier when I mentioned internal representations of the logic of those equations, the syntax and semantics. Not entirely sure how we'll walk through that yet. Given sufficient knowledge of the relationship, it would not be difficult to generate values and then leave one out. So that might be what we end up doing. So it would be easier to evaluate than to solve or symbolically on the fly as you're generating the problem. Another possibility is the computer doesn't know the answer and it checks when you submit it against the relationship to evaluate both sides of the equation. That could also be a way to get away with this without doing too much symbolic manipulation of the equation or the relationship. We could also have different permutations of that equation. So we explicitly say, here is one way to, given these values, what the value of pressure would be. Here's another way to solve for volume, etc. So that way you could choose permutations of the equation while generating the problem to use and evaluate to determine what the correct answer is or is not. Alternatively, we could go full symbolic. I don't know if that's something we're going to be doing in JavaScript in the front end. Maybe we could use Python and Python for that. Who knows? So you can see, based on the kind of or the type of relationship here, there are going to be a lot of different ways to model what that relationship is. And now we're getting in pretty deep. Now we're getting in deep enough that we probably want to pause for a moment. This is a lot for the first hack at this. So let's start with, in good software engineering goes inside out. You don't start with, the authentication layer. You don't start with the UI. You start with what is the core fundamental action or logic here. So let's define a function, generate problem. And let's, since we're saying we're starting with the units here, let's think about what the structure of that problem might be. Let's say given measurement x in units x, convert to measurement y in given units y. Okay, so let's say x is 10 milliliters, and then y is liters. And of course, we need to present a problem for which the solution will be the equivalent. So 1,000 milliliters in 1 liter. Did I do that right? Yes. Okay. So let's ignore this for a moment and think about how to structure this problem. So we want to, there will be some presentation of the problem, probably an enumeration of the parameters, and then some field for, submit solution and then evaluation of whether or not that solution is correct. So given the graph that we had that relationship already, keeping in mind that this would actually choose the relationship first. So let's pretend to draw the relationship from that mini database we had. So the relationship is, in this case, defined by, it had an ID, let's see, milliliters, 2 liters. It had a type, we called it a hierarchy. By the way, this is one potential way that sort of the recursive expansion could be used, is maybe you don't only want to evaluate to and from SI units, maybe you want to go from some non-SI to another non-SI, like centimeters to yards, right? Well, that means that you now have a 2-step recursive expansion of that problem. Internally, as you're trying to construct the relationship that's being evaluated, you have 2 relationships, coupled relationships you're considering. So the first would be, what did I say, inches to yards, centimeters to yards? The first would be the centimeters to meters question, conversion, that relationship. But instead of drawing a value for meters, you would then expand upon, choose another meters relationship, basically walk another step on that graph and say, well, there's a meters to yards relationship. Let's expand upon that. Now we can go centimeters to yards, implicitly converting through meters, right? So in this case, we'll only look at one relationship, but that's how you would do sort of the non-SI conversions. Technically, we had things like equation and other attributes of the relationship that we're not using for this particular type of relationship. So milliliters, keeping in mind that the to from here, since this is a relationship, a connection, an edge in a graph, basically these are the identifiers for the nodes, the relevant nodes in the graph. We have a factor. So this expresses the numerical relationship. So 2 liters from milliliters. If you're going from milliliters to liters, you multiply by 1,000th. Prefix, if we wanted to maybe define, mega, giga, centa questions. Not the sort of thing we're using right now, but it's possible. And then that's actually it. So how could we, given that relationship, draw up this question? Well, this is effectively a random value, right? So let's place some reasonable bounds on the random values we're generating, and let's say it's between 1/10 and 10. It's basically from -1 to +1. So that's going to be 0 to 1 times 2. That will be -1 to 1. 10 -1 to 1. So this is a random draw between 1.1 and 10. Speaking of which, these will all be positive values, right? In this case, you can't have a negative volume, so we're okay with that. But there may be other situations, and maybe that's another property of a measurement we need to find, is whether or not it's absolute, or whether, like speed, for example, it could potentially have negative values. In this case, so we have a relationship here. We will expand upon the nodes, the concepts. I think we called those just nodes here. So let's pretend that we've gone in and queried those relationships. Nodes in this case. So this is again coming from to and from, properties of the relationship. So the 2 node liters was defined by an ID Liters. We actually technically didn't include this one. We had meters. But the name would be liters. So, right. It has units. And what type is it? It's a unit. Okay, right. And then from, in this case is milliliters. Right. So by this point, we've pretended that we've drawn a particular relationship, and based on that relationship, we've drawn the relevant nodes. So this is from ID. This is to ID. So now let's construct the problem, right? And then we'll pretend so the problem is given measurement in units, what is the equivalent measurement in and you could usually see this being the result of some switch case evaluation of the relationship that we have. So this would be a different kind of query, a different kind of problem statement for an equation, for example, right? Same inputs, same outputs, just different types and different means of generating. So given measurement x, units x, what is the equivalent measurement in y? We don't have any dependencies here, so technically we could just run this if we wanted to. Evaluate this locally. Obviously, in the long run, I'm thinking of doing this as a website, probably just static files that will be hosted. For now, for testing purposes, we'll just debug in Node, see what happens here. So, given 7.1, maybe there's some degree of precision we need to track for these, right? What is the equivalent measurement in liters? Great. And then so we have, let's see. So the factor from 2 is, speaking of which, we could also basically just go backwards, right? Invert the factor and reverse the 2 from references. If we drew this relationship, maybe there's a coin toss to different which way we go at the beginning of problem generation. Given the solution value, measurement x, so relationship let's be kind. There's an error. Solution value result. Pretend this came from user. Obviously, we'll plug that in later. And divide by result. Oh, sorry, solution. We constructed procedurally. If the error is, this is a relative error, so let's say if relative is less than 1,000th, hundredths. Right. Or wrong. Okay, so we have a fixed answer here, so let's see. We'll need to show the terminal, huh? There we go. Low resolution code is. It's wrong. What do you know? Actually, let's change this a little bit so we can present the right answer. My kids would hate this. They are deathly afraid of getting the wrong answers on things. What do we say? Solution value. Voila. Okay, so we're procedurally generating problems now. Some degree of precision should be considered. Obviously, so the big changes from here would be we need to randomly draw the relationship. Based on that relationship, there's going to be some sort of switch case that actually determines how to choose the appropriate constraints, right? So this is technically a constraint. We're specifying a value for the x equals y relationship in order to find out y. And evaluate the solution differently depending on which variable and that relationship we choose to present as the degree of freedom. Depending on the relationship, the answer will be evaluated in a different way. For set memberships and multiple choice, obviously there won't be a relative error or any sort of error evaluated. It would be helpful to specify degrees of precision. A lot of things to do here, and that's even before we talk about sort of how to wrap this into an actual application of some kind. But you can see how this would be drawn from these data sets that we have. You can see how this could be folded into maybe there's 10 problems for a given topic area, and the user goes in to choose, give me 10 problems in the units area, or in the statics area, or in the fluids, or electronics area, etc. So now we have sort of the initial the beginnings outline of a knowledge graph and a way to use that knowledge graph to generate and explore different domains within the field of engineering. I won't necessarily write this out for each field of engineering we look at, but we will go through some of the more important and interesting concepts and relationships, and hopefully I'll keep this relatively up to date and maybe show some examples for how this concept in that field of engineering can be mapped to our knowledge graph representation so that you can look at it and try and study it without having a reference open. So that brings us to the end of our very first fundamentals of engineering stream. I hope you enjoy it. It seemed like a suitable transition. It's certainly a great topic area, and we'll be able to do a lot more sort of, I'd say we're calibrating this for like freshman, sophomore college engineering level content. It won't be enough for you to take and get like an EIT certification to take an exam, but it will be enough to get you started, and it will be enough for you to have a healthy understanding of different areas of engineering that you may not necessarily specialize in. And really, at the end of the day, that's my overall goal with this problem. We have a significant deficit of like core competency engineering and engineering execution projects and problems right now on large scopes for medium and large scale engineering projects. And I'm going to look at a little bit closer at that and sort of come up with ways to help alleviate understanding of engineering topics and areas, and hopefully have some fun conversations along the way. Take care.